In this video, we're going to look at some examples of calculating the truth values of complex sentences in PO. We'll use our simple mathematical interpretation again, same as from the last video. So start with this. So this is the main logical operator here is the negation, right? So this sentence is going to be true if this sentence in here is false. And then this is going to be false then if this formula here is not satisfied for any object in the universe of discourse. So for every object in the universe of discourse, GYY or LYY is going to be false. So Y is not going to be strictly less than itself, right? Uh, right, this one, or strictly greater than itself. So at this point, we can sort of piece together what this means in English, right? There is no number that is greater than itself or less than itself, strictly greater than itself, strictly less than itself. And that's true. So, we can determine that this is true. For our next example, we'll look at this. For all Z, EZ implies GZA. So this is universally quantified. So this is going to be true if this formula is satisfied by every object in the universe of discourse. So for every positive integer, if it's even, then it is greater than 1, right? Just remember that this is strictly greater than, and A is 1. This is a categorical sentence with a complex predicate term, right? If you remember from those earlier videos. So an idiomatic paraphrase of this would be basically this: every even number is greater than 1. And again, that's true, right? The smallest of the even numbers in this universe of discourse is 2. So every one of them is greater than 1. Okay, now we'll look at some sentences that have multiple quantifiers. So for all x, there is a y, gyx. So this is going to be true if this here, there is a y, gyx, is satisfied for every x in the universe of discourse. So, i.e., right, if for everything in the universe of discourse, there is some number that is greater than it, right? Some y that is greater than that x. Or here's a more idiomatic reading of it then. For every positive integer, there's some positive integer that is greater than it. And that's true. They go on forever. Now look at this one. This is the same sentence, except all we've done here is we just switched the quantifiers around. So now the existential is in front, and then the universal is embedded in here. Now this one is going to be true if there is at least one object in the universe of discourse for which this formula here is satisfied. So you have at least one object for which for all x, gyx is satisfied, meaning that for that object, right, for every x in the universe of discourse, that object is greater than x, right? Or to put it more idiomatically, if there is a positive integer that is greater than every positive integer. And that's false, right? There is no greatest positive integer. So this statement is not true. So you see that you get a significant shift in the meaning of the sentence just by changing the order of the quantifiers without changing anything else. Remember that in the very first class, I said that this sentence here was ambiguous, right? Everybody loves somebody. And the reason why it's ambiguous, I said, is that it doesn't specify whether everyone loves the same person or not. At this point, we can very precisely say what the ambiguity is, right? It's ambiguous whether it's this sentence or this sentence. So this one here says that for every x, there is a y such that x loves y, meaning that so for every person, there is somebody that that person loves, but not necessarily the same person, right? There just has to be somebody that they love. It could be a different person for each one. Some of these people could just love themselves and nobody else, etc. This one here says that there is somebody in the universe of discourse such that everyone in the universe of discourse loves them. This may be true, you know, possibly. It's certainly much more likely to be true than this. This is definitely false, right? It's not even true of Taylor Swift. We should probably get back to PL before I end up on a Swifty hit list again. Now look at something that's properly complicated. So let's take a look at this thing. Now, when you're dealing with something like this, it can be helpful to do a paraphrase as a sort of halfway step to figuring out what it means and giving an idiomatic reading of it in, in English or, some other natural language. Um, though bear in mind that there are sentences of PL that don't have idiomatic equivalents in English or other natural languages, right? So you may actually not be able to come up with an idiomatic version of it. Let's start with the paraphrase. So your paraphrase is going to be like this. Each x is such that if x is even, then there is a y such that y is less than x and y is odd. Okay, so in moving this towards something idiomatic, we can recognize that this is the structure here is like a categorical sentence. It's like an A sentence with a very complicated predicate term down here. But at least that tells us that this is going to start off with something like every even number, all even numbers, something like this. And then we're going to be getting into, right, all even numbers are such that there is y such that y is less than them and y is odd. Um, and eventually we should be able to work our way down to this, right? Every even number has an odd number that is less than it. Um, and that's true, right? For every even number, I mean, well, the smallest one of them is two, right? Two is greater than one. So one is less than two and one is odd. In fact, one is less than all of the odd, or so all of the even numbers. So they all have at least one odd number that's less than them. Okay, let's look at this then. This is similar in some ways. So the antecedent here is x is greater than one. Here's a paraphrase. Actually, let's start with the paraphrase. So the paraphrase is x is greater than, or the antecedent is x is greater than one. Consequent is, so there is a number that is less than x, and there is an odd number. And note that this may be a little easier to see in the original sentence than in the paraphrase. This here, these two are under separate quantifiers. They use the same variable, but that doesn't matter, right? The quantifiers don't overlap, right? They have like completely separate scope. There's nothing here that says that these are the same number, right? So what this is saying is that if x is greater than 1, then there is some number that is less than x, which is kind of obviously true, right? If x is greater than 1, then 1 is going to be less than x. And there's also a number that's odd, and it's not necessarily the same number because this is not under the same quantifier as this. So if we're trying to get something idiomatic, we're going to end up with something along these lines. For every number greater than 1, there is a number less than it, and there is an odd number. This is sort of an artificial way of putting it, but the thing is that this is a sentence that you actually can't put in idiomatic English. Because of the fact that you have this unrelated quantifier in the consequent of a quantified sentence, or a conditional that's in the scope of entirely within the scope of a quantifier. This is just not something that English does. Like you simply don't have this in English, and so you really can't actually express this idiomatically in English. What you need to do is basically the sort of artificial paraphrase style where, we're sort of just, describing the structure of the PL sentence. We are starting to hit the point with this of things that you can't properly talk about in idiomatic English because you can't get at the fact that this here is embedded in the consequent of a conditional rather than being something separate. At any rate, this sentence is also true, right? For every x, if x is greater than 1, then there's going to be a number that's less than it, namely 1. And in addition to that, there's going to be an odd number, lots of them.